What I want to cover today is a little bit more about hypothesis testing, because since that is the goal of this class, right? My number one goal is to teach you how to do hypothesis testing. So this way you can do it in future classes, in your public health classes, or in your political parties class, or whatever it is you guys are up to. We've talked about what the null hypothesis is. Essentially, the null hypothesis says that there is no relationship. But we're making that determination around our null hypothesis based upon an assumption. And I brought this out last class when we were talking about difference in means tests, and it was x bar 1 minus x bar 2, and then there was nothing in there for the population mean. And the reason there was nothing in there was because we had made an assumption that the difference in the two population means was 0. And this is where, again, the difference between statisticians who are good and people who will mention statistics incorrectly come in. Good statisticians understand probability. And they understand how much that probability theory is what is making all of this able to work. So what we're going to do today is talk a little bit about two types of probability and how we could get this wrong. So here's a scenario. You want to study the efficacy, that's actually the wrong word, the effectiveness of lie detector tests, which apparently I'm learning, like the guy that created Wonder Woman actually was working on this at the same time, the whole lasso of truth thing. I don't know, I gotta watch that movie. So let's do a test on the effectiveness of polygraphs. Let's interrogate 68 suspects, and under a polygraph, and let's compare the results of the polygraph, which is going to tell us whether we think they're guilty or not, versus whether they were actually guilty or not. So if the polygraph says you're guilty, there are two possible outcomes. You are actually guilty. This is a good outcome, right? You did what the polygraph says you did. Polygraph correct. There's also a possibility that the polygraph says you're guilty, but you didn't do anything. You just apparently are one of those people that's really bad at taking tests, which also is not a thing. All right. The polygraph can also say that you're not guilty. But of those people that the polygraph says are not guilty, there could be some people who are innocent. And so again, polygraph gets it right. But there could be a situation where the polygraph says you're not guilty, but you really did it. So what did you do in this situation? How do we colloquially say you have done something? You have what the test? You beat the test, right? Like it's somehow you versus machine. Like this is a skill you have. Oh yeah, I'm really good at beating polygraphs. Okay. So of these four outcomes, how many of them do we think are good? How many of them are bad? Yeah. So we have like a 50-50 scenario here, right? 50-50 good, 50-50 bad. So here's the results of that study. Overall, are we happy with the effectiveness of a polygraph? Well, if the polygraph said you were guilty, how frequently were you guilty? 16 out of 17. You can turn that into a probability, right? That's a percentage. 16 out of 17. How frequently did the polygraph say you were guilty when you were actually innocent? 1 out of 17. Okay. Let's do the reverse. The polygraph says you're not guilty. What's the probability that you were innocent? 37 out of 51. That's pretty good. Wait a minute, that's 60-something%. 14 people were actually guilty. 14 out of 51. That's like 29%.
Pretty good margin of error.
That's not good, right? Okay. Of these two, which one do you think is worse? To say that somebody is guilty when they're not, or to say that somebody is not guilty when they are?
Guilty when they're not.
All right, one at a time.
Guilty when they're not.
You think it's worse to say that someone is guilty when they're not?
I agree. Yes.
You agree? You agree? Anybody disagree? Why?
Because you actually didn't do it, but you're gonna take the fall for it.
You're going to get what? You're going to get punished.
Right. I mean, that's like a death penalty. If you didn't kill that man, now you're gonna die.
Perhaps the death penalty. Okay, not that we ever convict. Oh well, sometimes it might have happened once. Okay, so that's bad, right? That we agree that that is worse than letting some guilty people go, which is not our preferred outcome, right? Because we want guilty people to go to jail, or be punished, or pay a fine, or get slapped, or something, right? But we really don't want to like kill an innocent person. Okay.
Then again, the guilty people that got innocent will come back and kill innocent people.
Yeah, my dad used to be a cop, and he's like, "Don't worry about it. Criminals are stupid. It's like if we don't get you for one thing, we'll get them for something else." It's like, "Oh, okay, thanks, Dad. That's really good." It's like some version of karma. Like, we might not catch him on this one, but we'll get him on the next murder. Good job. Okay. I've alluded to this before, but really what we have here are two distinct types of errors. And quite frankly, because we're built on probability and not on physics being determined, in social science we're going to make errors. It's going to happen. These two types of error, type 1 error is when you say there's an effect. Right? We're rejecting the null hypothesis. That's type 1 error. We're rejecting the null hypothesis when we should not, because it's true. So type 1 error, you say there's an effect when there is not one. The other type of error is type 2 error. You should say there's an effect, because there is one, but you don't. Now we said before, under our example of the lie detector and the crimes, that type 1 error was the worst, because you're really truly innocent and you're going to be punished because the test is wrong. Well, this goes back to that same idea. Type 1 error still is the worst type of error. To say that there's a relationship between two things when in fact there isn't. So if we're in biochem and we're testing a drug to see what the effect the drug has, would we rather say that a drug helps cure cancer, or say that the drug doesn't cure cancer when it actually does? Which is worse? Well, in this one, we actually still think it's worse. Type 1 error. Why? Because if I tell you to take this drug and you'll be cured, what happens to you? You die. And you also just take that drug, you might not seek out alternative treatment. So for something like cancer, you have chemotherapy, you have radiation, you have surgery, right? You have alternatives. But if I say, here, take this rock and put it in your pocket, it'll cure your cancer. And you do that, you are giving up the opportunity. Economics has something called opportunity costs. you're giving up the opportunity to actually receive the correct treatment. Whereas with type 2 error, if I conclude that the rock in your pocket does not cure cancer, when in fact it actually does, you will still seek out treatment. You just won't have the life-saving benefits of the rock in your pocket. And by the way, I totally stole that example from an episode of The Simpsons. Lisa gave her dad a rock that keeps bears away. And she's trying to explain to him causality, and he's like, listen, I don't care about that thing, but how much can I pay you for that rock?
They do predict the future a lot.
Okay. It's just a 20-something seasons, good thing to steal. Okay. So type 1 error, that's the one we want to avoid. So how can we avoid it? Well, we kind of already know the answer to this. It's called our alpha, right? We constructively decide how much type 1 error we're willing to accept. And this is our decision rule. So social science has said 5%. If we set our critical values so that there is 5% in the region of rejection, that leaves us with a 5% chance that we will reject a null hypothesis when we shouldn't. At most, 5% chance. But it is a 5% chance. But if you reverse that, that means that there's a 95% chance of not making an error. This is where framing is important. Right? Instead of the 5% of bad, there's still 95% of good. There's a 95% chance that our sample gives us an accurate reflection of what's happening in the population. That's pretty good. I'll take that. Yeah. Why does it happen? This is where I get to talk to you about eating soup. This is also an opportunity for me to tell you one of my favorite words in the world. Stochastic. Anybody heard of stochastic before? Or stochasticity? It's scholastic. Those suckers get a ton of money from me every month. That's why I have a kid that likes to read. Stochastic. Nobody's ever heard of that? This is like my life theory. Life is stochastic. Life is random. It's completely random. You go down to your car at the end of the day, what's the chance that it turns on when you put the key in? Is it 100%? No. It's never 100%. Eventually, as your car gets older, like you just start praying, right? Please, Lord. Please, baby Jesus. Please, hippie Jesus. Let my car start. All the G's please let my car start. Because there is a amount of randomness to our lives. And we have zero control over it. We can try, right? Let's say we're really, really paranoid about our car starting. What's the most extreme thing we can do to make sure that every time we go to a car, it starts? Yeah, we could like replace our starter every night. All right, I'm going to go home. I'm going to take out the battery, the alternator, and the starter. And I'm just going to put a new one every day.
At this point, you mess up more often because you got to mess up trying to install something.
Well, you could get really good at it too, right?
But then your wires.
Okay. So life itself is stochastic. But there are things we can do to reduce the amount of chance and randomness in our statistics. And I can explain this through soup. I guarantee that most of you in this class eat soup incorrectly.
Okay.
Did you know that there's a right way and a wrong way to eat soup? No, that's not anything to do with handedness. If I give you a bowl of soup, and it is the perfect temperature, put it down in front of you, Alex. And I hand you a spoon. And it's the perfect size spoon. It's not too big, like you gotta go, ah. It's not too small, it's not gonna fit on it. It's the perfect size spoon. It's not like one of those sharp plastic spoons either. I hate those. Right? And I say, eat your soup. What's your favorite kind of soup?
I don't know, it's tough.
Top two.
Chicken noodle soup.
Yeah, everybody goes with chicken noodle.
Clam chowder.
I'm more of a chowder guy, but I understand. Okay, so whether it's clam chowder or chicken noodle soup, I hand you a spoon, you're hungry, you say thank you, you have a napkin. How do you eat your soup?
I just put the spoon in the bowl and just.
Scoop of soup, right?
Yeah.
Yeah, that's wrong. That's wrong. You actually eat your soup incorrectly. And if you all agree with Alex, you are actually.
I'm like barbaric.
You drink your soup? That's also incorrect.
Okay.
That's also wrong.
The
Stick your hand in.
no cupping. The correct way to eat a scoop of soup is to put your spoon in the bowl and don't lift up. Don't do that. That's the mistake you make. Stir. Why do you need to stir chicken noodle soup?
It heats it.
No.
Spreads everything evenly.
There you go. Jeff's got it. What do you really want when you're eating chicken noodle soup?
The perfect amount of noodles and chicken and everything.
Yeah, that scoop better have noodles. It's the first time you've talked all year.
Ratio.
And he's like, and he's got it. He's like, I know this. I can speak to this. First time all year, he's like, I got this. Yes, you are absolutely correct. The thing you want is every ingredient on your spoon. Because what happens if I hand you chicken noodle soup and you don't stir it? What do you get? You just get broth. That's also why it's wrong to drink it, because you're just going to drink all the broth first, and then you're going to get like a wave of noodles in your face. You need to stir your soup. Stirring reduces chance. Okay? It reduces the separation between the broth and all the good stuff that is sunk to the bottom. Because noodles don't really float. Okay? Chicken, it all sinks to the bottom. And that's the part you really want. You're tricked into eating the healthier broth than the stuff at the bottom. So why does type 1 error occur? Very simply, you screw up. You screw up. You eat your soup wrong. You do your sample incorrectly. Some of it is due to chance. Because again, remember, we treat the pot of soup like a population, and we take a sample of that population, whether it's a bowl of soup or a scoop of soup, depending upon the size. We know that we could just get broth. Especially if my kids are the ones doing the soup. Because A, Abigail doesn't understand what a slotted spoon is versus a ladle. And so when Abby's like, oh, I'll get the soup, I'm like, well, no, you won't, because you know how to do this. Because what does she do? She goes and grabs the slotted spoon. It's like, that's great if you don't want any broth. She puts the slotted spoon in, all this broth runs through the slots in the spoon, and then she dumps the noodles and the chicken. And that's really what she wants. She doesn't want chicken noodle soup. She just wants chicken and noodles. That's all she wants. If you give John the ladle, John's like, oh, okay, but he's small. He doesn't understand to stir the soup, so he just dumps it in, fills up the ladle, and all you get is broth. A person as smart as me has to train my kids how to do soup. But it's okay because you all are doing it wrong too, I guess. When we set up a research design, we have to make sure we're doing it the right way. So we want to minimize chance as much as possible, because chance is what we have, right? A sample is chance. It's that 100 people out of the 300 million that are in the world. So you have to reduce chance as much as you can. Type 2 error, the null hypothesis is false, but we failed to reject it. We denote the probability of making a type 2 error as beta, and I hate that. Because we use that beta for like 3 other things in statistics. I mean, I get alpha is the first letter, beta is the second letter, 1 and 2. But we use beta for other things. So I'm just going to warn you. Beta's out there. The problem is that we don't actually know what beta is. We decide what alpha is going to be when we set our decision rule. But we don't actually know what beta is. Because we don't often know the true population values. If we knew the true population values, we wouldn't have to do inferential statistics. We wouldn't have to take a sample. You take the SAT or LSAT or ACT, they know the population because they know the score of every person who took that test. When they tell you you're in the 92nd percentile, they can do that because they know. But if we're talking about abortion policy or tax policy, we don't know what the population's viewpoint is because we don't have access to the information about the population. So beta is a little bit more difficult. There's a concept called statistical power, the power of a test. And the power of a test is the ability to detect an effect when it does not exist in the population. This isn't something that we think about a lot. We know it's out there, but for the most part, we're mostly concerned with that type 1 error as researchers, because we don't want to say a relationship exists where one doesn't. The reason we're most concerned about that and not type 2 error is because type 2 error comes about because of chance. Right? It comes about because something we've done is wrong or our sample's not big enough. Right? So why does it happen? Because of chance. Because we have a small sample. Because we have something wrong with our research design. We're not measuring the effect appropriately. That's why we can't say that it exists. This is a good example where I can actually point to the hard sciences and think about the evolution of measurement over the past, I don't know, 500 years. So imagine you're an astronomer 500 years ago. How do you study the stars? Like, you just look up in the sky, right? You're an astronomer today. How do you study the stars? Yeah, you can launch vehicles into space to take pictures for you and transmit them back.
Read information across the globe. Exactly.
Yeah. Over time, our ability to measure gets better. We can see farther into space. We can see different, 500 years ago, we're limited to only what you can see with your naked eye. Now we've got all sorts of sensors that can do infrared and radiation and gravity, and like, you can look at things not just through your eye anymore. So measurement gets better. You could have, again, if you're studying astronomy 500 years ago, you're making lots of type 2 errors. You're not noticing effects that exist. And it's just a research design issue. The fact that you have to use your eye, or if you're lucky, a telescope, versus a massive satellite that costs a couple billions of dollars. People hated the fact that we spent so much money on Hubble. And it's great because NASA actually gives us the most return for our value. Like, you look at the amount of money we spent on wars versus what we spent on one satellite, and the things we have learned from Hubble or a Mars Explorer, or like, just totally outweigh the fact that, you know, will just cost like millions of people their lives. All because the science gets better. Okay. So we've learned this, okay? This is what we've done today. Type 1 error, that's the guilty person who is actually innocent. We have control over that. That's our alpha. Type 2 error, the effects that we miss, don't have a huge amount of control of that. That's where chance comes in. But it's not something we can directly measure. It's hard to observe something when you don't know it exists. So you can drive home today, and you can know that you almost didn't die because that car finally stopped. That you notice. We almost get killed all the time, and you don't even notice it. The things you don't notice. All right. How do we control for this? For alpha, it's easy. You just control what you set for the decision value. The problem, though, and this is the takeaway about the relationship between alpha and beta. So if you think about it for a second, if you make it harder to reject the null hypothesis, you're also making it more likely that you commit a type 2 error and don't reject the null hypothesis when you're supposed to. So that's why it kind of bothers me when we talk about the difference between 0.05 and 0.01 and 0.001 and all the other stars, right? We're okay with that 95%. We're okay with the 95% getting it right. That seems like a good number for us. We're also okay with the 5% chance that we make a mistake. If we make alpha higher, or I guess technically alpha lower, making it smaller, right? That increases the chance that we're going to make a type 2 error, and beta actually goes up. So if alpha goes up, beta goes down. If alpha goes down, beta goes up. What can we do? Best thing for type 2 error? Make it more likely to reject the null. Make it more likely to be able to see a difference. How can we do that? Easiest way for you guys is to raise the sample size. So back to the data set that we were doing earlier with Hampton, right? Looking at the SDA. That GSS has been around since 1974. So let's say you do your paper, and we in the social sciences tend to only like to look at new data. So let's say you only look at the 2016 data. You run your analysis and you find that there's no effect. Well, I'm thinking, well, you don't even know how to eat soup. You've done another mistake. You've ignored all of that previous data. Go back. Run your test in 1974. Run it in 1982. Run it in 1990. See if over time there was an effect. Or throw it all together in one big data file, which is the default for that website. So when you look at your data set, you'll notice that you have like 62,000 variables, or 62,000 observations for your variable. That's a good thing if you're trying to reject the null hypothesis. and not make a type 2 error. The other thing you can do, and I've sort of said be careful about this, is to use a directional alternative hypothesis. Right? Go ahead and say, listen, I am fairly certain that my 5% should be in this tail. And explain why. Sample size is important, and I'm going to stop there.